We're beginning Unit 5, which is about conservation laws. Conservation laws are a completely different way to analyze physics problems, a more sophisticated way, often in scenarios where the details of the forces or the accelerations are too complicated to track in every individual second. If we wanted to analyze how the force changed from second to second to second to second, in principle, we could figure out the acceleration every moment and then integrate that as a differential equation and then figure out the overall motion of an object. But there are easier ways. We can look at how the objects in a system of objects behave before they interact and then after they interact, and look at some quantity that is supposed to remain constant during their entire period of interaction. And then from that quantity, figure out how they had to have changed. And the two particular quantities that we're going to be looking at through this unit are things that you might have heard before. They're momentum and energy. We're going to start with this idea of momentum, and in order to build up to that, we're going to have to define momentum. And in order to define that, we're going to have to define something called an impulse. So let's look at a scenario where impulse is appropriate, and it starts with a well-named impulsive force. So an impulsive force is one that occurs over a short duration. So here we have someone kicking a soccer ball, and the soccer ball, the contact with the foot and the soccer ball begins at 30 milliseconds, and as the foot compresses the soccer ball, you get more and more force, and the soccer ball begins to fly away from the foot, and you get less and less force, and then finally the soccer ball leaves the foot at 70 milliseconds. So this is an impulsive force because it occurs only over a finite duration. Also, it has a kind of a complicated shape, right? Just like I spoke of before, you wouldn't want to try to figure out the acceleration at every individual point of time for this force. So it would be handy if we had some way to analyze the interaction between the foot and the soccer ball that didn't rely on this moment-by-moment calculation of acceleration. So in order to figure this out, we're going to define a couple of quantities. And this first quantity is called an impulse. So impulse, first of all, is denoted by the letter J. That's not my fault. That's just what happens. So the letter J is a vector, and so it points in a direction in space. So it could be left, right, up, down, left 30 degrees of up, etc. And it's defined as the average force times the duration of contact of that force. So just like with the soccer ball only occurred for 40 milliseconds, if you knew the average force times the duration, you would be able to calculate that. If you knew some calculus, there's another way to calculate that, but we are not doing a calculus-based course. The word integral is involved. So, the impulse is a calculation of the total overall effect of the force as it's applied to the object during that duration of time. So what does it actually do? Well, we're going to do a calculation to figure that out. So we know that the definition of impulse is given here. It's an average force times delta t. Okay? And we know that if we have one force on an object or a net force on an object, that is equal to mass times an acceleration. In this case, since we have an average force, it's going to be an average acceleration. And furthermore, if we have an average acceleration, that's going to be equal to a final velocity minus an initial velocity over a duration. So we're going to put these two together over here. And so we're going to have impulse is equal to our mass times our acceleration, so our final velocity minus our initial velocity over our delta t. And we're going to multiply that by the delta t that we have on the outside. And you can see that these delta t's are going to cancel each other out. And so that we have impulse is going to be equal to mass times our change in velocity. There's a vector right there too. We could leave it like this, and it's often convenient to when we're actually applying it, but I'm going to distribute it so we can look at this quantity here. Impulse is equal to a mass times a final velocity minus a mass times an initial velocity. So if we had a quantity that was a mass times a velocity, and we were to name that quantity, I don't know, let's just come up with a letter P. And this were a letter Pi. Then we could write that the impulse is equal to a change in that letter, right? Well, it turns out that some people already did that. And they called that letter P momentum. It's also not my fault. That's just the letter they give it. M was already taken. I was already taken too for impulse. We just skipped that section. It stands for rotational inertia. So this is the impulse momentum theorem. It tells us how an outside force applied during a certain amount of time, the delta t during its contact, changes the overall motion of an object, its momentum. And we have different ways of just rewriting that equation conveniently depending on what information we have. In this class, the mass is rarely changing, so we could rewrite it in this form here. We're usually interested in trying to figure out how the velocity changes. So let's look at an example. We have a tennis ball flying to the left, 30 meters per second. It gets hit by a tennis racket, and afterwards it's flying to the right at 42 meters per second. We know that the ball was in contact with the racket for 0.120 seconds. So what is the average force of the racket on the ball? So the first thing we want to do is draw a picture. Here's the ball flying to the left at 30.0 meters per second. We have the racket. Afterwards, it flies to the right at 42.0 meters per second. It has a mass of 0.100 kilograms. And along with our picture, the most important thing in all momentum problems that we need to do is establish our coordinate system so we get the signs of everything correct. We're also told that delta t is equal to 0.120 seconds. Okay, so we want to use the equation J is equal to delta P in order to figure out J. And so this is the impulse momentum theorem. And then we're going to use J equals F average times delta T to get F average. And this is the definition of impulse. Okay. So let's put those together. Of course, we could just put them together right here and say F average times delta t is equal to delta p. And I get F average is equal to delta p over delta t. What is our delta p that we want to put in there? So delta p is going to be a mass times a change in velocity. If you remember, that was one of the forms that we could put in for our impulse. Okay, this is the most important step. We're going to put in our mass. And when we put in the velocity, we have to keep track of the signs. So our final velocity, remember this is final minus initial, our final velocity is a positive 42.0 meters per second minus, and our initial is a negative 30.0 meters per second. And so our change in momentum is 0.1 times 42 plus 30. I didn't need a calculator for that, but there we go. So we have 7.2. Now let's think about the units. So the velocity has meters per second. The mass has kilograms. And so we just multiply those units together. We get a kilogram times meters per second. And it's kind of hard to interpret what that unit is outside of just thinking of what that quantity means, right? So momentum itself is telling you not just how fast it's going, but also how much mass it has. And so the units are just repeating that information. There's no further detail by which you can interpret what those units are. So they just hang out. They don't simplify into anything. We don't call that unit anything. If you want to think of it this way, you could write that as newtons times seconds. I'll leave that to you to calculate. But I don't find that much nicer to write than those, so either one. Okay, so now we're going to put this value up here. We see that F average is equal to 7.20 kilogram meters per second over 0.120 seconds. And we get 7.2 divided by 0.12, and we get 60.0 newtons is the average force on the tennis ball.